All right, great, thank you. So I will try to limit my presentation to about an hour or so. I don't have too many slides, and I'll try to see if I can be as eloquent as Subbu here. I don't see him here. But if you have any questions during the talk, please let me know. I'd like this to be more of an interactive session than actually a lecture, because I really think that we are living in a golden era of exoplanets. Many of you have grown up in this era of exoplanet boom. Some of us did not. We did not even know there were planets. So that tells us about what our age is. I'm not going to talk about it. And so the fundamental questions of finding exoplanets, their properties, their characterization, eventually we'll have to answer one of the most important questions for our humankind, which is to find life on extraterrestrial worlds. When I say life on extraterrestrial planet worlds, it could be anything beyond Earth, not even not just beyond the solar system, even within the solar system. I'm sure we will hear from Sudha in the afternoon about biosignatures on Earth and probably within the solar system. I'm not sure if anyone is talking about life signatures within the solar system, but my talk would be mostly focused on exoplanet life signatures. I don't know how many of you have attended a few years ago, we had this lecture series a couple of years ago, and I showed the same slide and the same title. And I couldn't find a better title than this, because this is literally what we are trying to look for currently with all the kinds of missions that Subbu discussed or you guys have seen in this week. That's exoplanet life signatures. Life could be anything. It could be biology, it could be technology. And so in this particular presentation, I'm going to discuss both kinds of life. How do we detect them? What is the current status? And how soon are we going to detect this kind of life? I think I can make this bold statement that within our lifetime, we will be able to find extraterrestrial life. It is not a question of if, it is a question of when we will be doing it. Certainly in your lifetime, the young generation's lifetime, you will be able to see extraterrestrial life. Because you can see these signs of getting to that point. Every major discovery starts with false positives. Someone claims some kind of thing, and then someone refutes it, and someone else comes and makes another claim, and then someone refutes it, and eventually that becomes a reality. This is what happened to the exoplanet discovery as well. I don't know if anybody has discussed the history of exoplanets in this lecture series. If not, there were many false positives before the actual exoplanets were discovered, right from the last 100 years. Even the hot Jupiters were predicted back in the 1950s by Otto Struve. At that time, he mentioned that you can use radial velocity techniques to detect these hot Jupiters. Everybody ignored it. That paper back in 1952. And then people were surprised when the first exoplanet was, the first exoplanet around a main sequence stars was discovered around a hot Jupiter planet. Before that, it was also a pulsar planet. That's also an anomaly. And so we will see, and before all these discoveries, there were false positives in the sense that there were claims of discovery of planets around other stars, but eventually they were refuted, and eventually these things became reality. We are in the similar stage right now for the exoplanet life signatures. There are claims of detection of life on different kinds of planets, on Venus, on exoplanets, but there is a debate about it. There's a controversy about it. But that's the reason I'm confident that within our lifetime, we will be able to see some kind of evidence for extraterrestrial life. All right. And so the definitions that I want to follow in this talk related to signatures of life are related to biology and technology, biosignatures and technosignatures. These two definitions that I'm showing here are from NASA's definition of life. This is one definition of what we define as a biosignature and a technosignature. And that doesn't mean that this is the only kind of definition that we will be follow. But we need a template of definition to identify and define our mission goals for detection purposes. And so for this purpose, a biosignature is an element, molecule, or a substance or a feature that can be used as evidence for past or present life. We have crafted this definition not just for exoplanets, but also for in situ measurements or for Martian life detection and so on. That's why the definition includes biosignatures, any element or a molecule, because that's something that you can actually go and dig and analyze and get a sample on. Whereas a feature is something that you can actually use detect using a remote detection techniques like we use in exoplanet atmospheric characterization. And that's for a biosignature. Essentially, you can use the same definition of biosignature for a technosignature as well. Who is trying to find the life? Not the microbial life. Microbial life is not trying to find microbial life. A technological civilization is trying to find biology. A technological civilization is trying to find life on other planets. So it makes sense to look for technology. So the technology is trying to find technology. And that's why it is also important to look for technosignatures. There is another reason for that. Whenever we point a telescope, a new instrument, a new tool towards the skies, we have always found something unexpected. I'll come to this at the end of my talk. And so when we never know what we will find when we actually build a telescope and point to these outside planets. And so we can use the same definition of biosignature for a technosignature, but we'll make it a little bit simplified here. It says that a technosignature is an observational manifestation of a technological civilization, either past or present. You may be wondering, what's this past doing over here? It could be a compound for in situ measurement purposes. For remote detection purposes, it could be a group of compounds that you can detect to identify as a biosignature. That's a good question. A single element or a molecule or a substance is not a biosignature. Okay, there are so many ways nature can fool us to create these abiotically false positives. And so whenever someone claims that, okay, I found a biosignature element or a compound or a substance, and I think I found life, you have to be really careful about analyzing that kind of a result or understanding that kind of a result. Life produces various chemicals. It doesn't produce only one chemical as a signature of life. And so we need to make sure to understand the context in which that signature was analyzed or detected, and then make a judgment about whether that detection is valid or not. And that's where there's also false negative, which is that there may be a signal there, but we dismiss it because we don't think that it is valid because the signal to noise ratio is below 3 sigma or whatever. And so we need to be careful in judgment. But eventually, science will win. Eventually, we will find it. If it is a real signal, there is no way we will miss it. And so for both the biosignature and technosignature, identifying these kind of evidence, evaluating, getting consensus from the community, independent investigations, independent data analysis is the only way we can actually identify a real good signal. Okay, so as I said, we will be discussing only remote detection of exoplanet bio and technosignatures and not in situ measurements of solar system biosignatures. Maybe Sudha will talk about this in her presentation, but the remote detection aspect of this exoplanet bio and technosignatures makes it a little more difficult because all we get from the planet or from the star is just the light that's coming from them. And that's all we have right now. And that's all we can use to analyze and make conclusions on the kind of detection we are going to make. And so the entire industry of exoplanet biosignatures and technosignatures is based on analyzing a spectrum of radiation coming from the star or the planet, remotely detecting, and then using models, climate models, photochemistry models, these kind of models, atmospheric models to analyze that kind of, combined with these observations to get to a conclusion of whether there is life or not. All right. This, before we begin, there is a particular definition of life signatures what we want to make. That's the definition of the habitable zone. And there is a reason why we have to define this particular aspect of exoplanet life signatures, because if we are going to find life on these planets, we need to know where to look for these planets, where we need to look for life on these planets. I think Subbu mentioned this statistics and probably showed even a graph where there are thousands and thousands of planets out there. Now, which one of them we will be able to target? What kind of a telescope you're going to build to look at which planet out of thousands? We don't have enough time on any of the telescope. We don't have enough resources. We don't have enough ground-based telescopes to look at all those planets. So to narrow down those kind of planets where we can focus on to find these biosignatures or technosignatures, we need to define a region around a star where we think that life could sustain. Now, how do we go about from there? How do we define that region? Well, one of the things is we'll look at Earth and see that, okay, where is Earth located right now from the sun? Well, it's not too close to the star, because Venus, we know what happened to Venus. It's quite hot. It's not too far away from the star. Mars, well, Mars is pretty cold. There are other complications there. But it is at the right distance, and that's the habitable zone. It's in a zone around a star where there could, if given enough appropriate atmospheric conditions, pressures, temperatures, composition, we could have a potential life on the planet, or potential habitable region, or habitability on the planet. There is that definition of the habitable zone is what I've listed over here. It's the region around a star where a terrestrial size or mass planet with a suitable atmosphere, you can see the suitable in quotations there for a good reason, with a suitable atmosphere can maintain liquid water on its surface. You see how politically correct this definition is? There is a good reason for that as well. And I mean, you can break every part of this sentence is controversial. Why it has to be a terrestrial mass planet? Why can't a Jupiter-sized planet, a gas giant, be habitable in the upper atmospheres or wherever it could be? You know, could be possible. But we know Earth. Earth is not a gas giant. Okay, fine. Then we'll focus on terrestrial mass planet. What is a suitable atmosphere? Well, it should have a 1 bar or whatever. That's the kind of atmosphere we have. Not too high pressure, because Venus has high pressure and we know that there is probably not life. Not too low pressure. We know Mars doesn't have a dense atmosphere. It's 6 millibar atmosphere. So it should have about the right kind of atmosphere like Earth. Good. Okay, fine. So that's an Earth kind of atmosphere. Oh, also, by the way, it also should have nitrogen, oxygen composition atmosphere, because that's what we are, right? Okay, fine. That's a great one. See where it's going. And it should maintain liquid water on its surface. Why liquid water? Why on its surface? Because Earth has liquid water and it's on the surface. You see what we are doing here? We are taking Earth as a template and trying to project the same kind of conditions that we want to look for an Earth-like planet around other stars. Why should we look for Earth-like planet? Why can't we look for non-Earth-like planet but still have life on them? Here's a comparison. Let's say you're invited to a party. You don't know who they are, but you got an invitation. And you go there. What is the first thing you do? You go and see the most familiar person first. And then you go and talk to them. That's what I did here. First, when I came here, I first saw Joe and Jayesh. And I go and talk with them. And then I met everyone else. That's what we are doing. We're going to find the Earth first. We want to find Earth-like condition because that's what we can recognize. If we find something that is not Earth-like, but still has life, we will not be able to recognize it has life or not, because our minds, our brains are not evolved to find something unexpected. And so even with our all machine learning and AI, maybe they can do it. However, for us, to build a mission, we need to define the characteristics of a planet that we want to look for. And that's what is Earth is, because that's what we know very well. And that's why we focus so much of that definition on Earth-like conditions. And so a liquid, will come to the liquid water and on its surface a little bit later. Another point here is that this definition of habitable zone has little to do with habitability. There is a difference between habitability and inhabitants. Habitability is having the right conditions to have liquid water on the surface, according to this definition. Inhabitants is, yes, the planet is habitable, it has liquid water. However, it should also have life. That's inhabitants, or having a life on it, on the planet. And so this definition of the habitable zone has nothing to do with habitability. It's only the reason why we want to have it is more for target selection. If I see a planet around a star, if I know the amount of radiation that's impinging on the planet, because that's the only thing I can measure. I know the star's luminosity. I know how far the planet is from the star. I know the distance. I can divide the luminosity over distance square. I know how much flux the planet is receiving. I'll compare that flux to my flux here on the Earth. If it is more, it's not habitable probably. If it is less, probably not habitable. So I'll ignore that planet and move on to a planet where the flux is comparison to my flux here from the sun. And so it is more for target selection and remote observations. Yes, Priyanka. Correct, actually, because the moons around giant planets, they probably could be habitable, like Pandora in Avatar. Could be. I never think that those kind of planets could exist for a good reason. If you have a moon around a giant planet, it might be very tidally active, just like our Jovian moons, and so they might be habitable, but they will be out. And you might say, oh, we will miss it. Yes, we will miss it. Not everything has to be discovered by humans, right? So it's what it is. And we don't have the telescope technology. In fact, even it's worse than that. If you are building a telescope to look for Earth-like planets and you're finding giant planet and a moon, the signal will be combined together because the giant planet just dominates whatever the signal. What is that signal? It could be infrared excess coming from the planet. It could be the albedo measurements coming from the planet. You might see some faint imprint of the moon on it, but your telescope has to be really good to actually identify and distinguish between them. So yes, we will miss those kind of moons. Good question and good point as well. So I'll repeat the question here. The question or the suggestion here is that moon is essential. Any satellite, natural satellite is essential for habitability of a planet, right? Right. And so we should be able to consider that as well. However, that step comes later on once we actually know what kind of a mission we want to to build. We cannot build a telescope based on the fact that, oh, a moon we want to look for signatures of life on a moon. We want to first look for a large signal because that's what our telescopes are most sensitive to. The fact of how moon affects the habitability of a planet comes later on. And that's what I was trying to mention here, that once you detect a signal from, let's say, a habitable zone planet, we will not know if that planet has a moon or not, because the signal will be combined together. And if you build a model, a climate model, and then try to match your observations with the model. And after matching everything, if there is still some excess signal coming from it that you cannot explain, then you can attribute it to, oh, probably the planet has a moon. Does that make sense? Okay. Yes, please, and go.
Just a follow-up. The moon helps in sort of keeping
No, stabilizing the climate. And so, for example, if moon wasn't there here, I think probably our obliquity would be varying so much that it probably would have not been possible to have a stable, habitable climate. Is something that some people mention that, because the obliquity would be varying so much and the seasons would be so vastly varying that at any given point you would not probably have a sustained stable, habitable climate, like completely snowball episodes for millions of years, and then suddenly you have no ice and complete water world, all continents, immersed in that oceans, or something, planet may be super hot. Several times, it may happen several times. Mars probably went through that actually, and that's the one that she's referring to. It's the obliquity variation effect by the moon. It's the age of the system, age of the star. If we know the age of the star, then, oh, are you referring to, it takes some time for life to evolve? Yeah, it does matter. However, when we identify targets, let's say we identify a few targets, and if we can find the age of the star or the age of the system, then we can make an educated guess about whether there could be life or not. But the only thing that can actually answer that question is actually observe them. Because our assumptions about how much long the life will take is very limited to Earth itself. There is no need for a life, and I'll come to that in a minute. There is no reason for life on other planets to evolve in the same situation, in the same way, in the same time scale. And there's a good reason for that as well. Let me come to that, and then you'll see why that is important. Okay, so this definition is more related for target selection rather than a statement about life on the planet. By the way, whenever I talk about the habitable zone, many questions come up on, hey, how about life that's subsurface, like on Europe or Ganymede or something? How do you know there is life could be there on Europe or Ganymede? Oh, well, because we know there is subsurface oceans on these moons, Jovian moons. Okay, how did you find those? Oh, well, we sent probes onto them. Oh, okay, can you send probes to exoplanets? No. There you go. It's all about remote detection. This entire definition is about remotely detecting life. And why surface liquid water? Why surface? Because the assumption is that if you have surface liquid water, there could be potential life that could potentially emit some sort of gases into its atmosphere that we can detect using our telescopes through spectroscopic observations. And if you see those kind of biological gases in the atmosphere, signs of these gases in the atmosphere, you could conclude potentially that there could be potential life that is emitting these gases. If there is subsurface life, hundreds of kilometers or even tens of kilometers, hundreds of meters below the surface of a planet like Europa or Ganymede, super Europa or super Ganymede, it is not clear whether that kind of life can release any biosignature gases that could come to the surface that we could potentially detect, passing through all those layers of interior layers and come up and then see if we can find with our telescope. And that is why this definition of the habitable zone includes only the surface liquid water. And then people may say, okay, then we will be missing all those planets subsurface. Yes, we will miss it. There is no reason for us to, universe doesn't give a damn about whether we want to detect or not. It is our need to find life on other planets. And this is the first step in the human history we are trying to make it. And this is the reason why we will focus on simple things first. And then eventually when we, I guess, develop warp drive, we can go to those planets, dig, and see if there is surface life on them or not, okay? All right, so why liquid water? I think some of you may have seen it or guessed it. Water is a polar molecule. It's a universal solvent, can mix with everything, almost form bonds with almost all other chemical, and then forms chemical reactions. It has also 3 degrees of freedom, and so it is very active in the infrared part of the radiation and could be easily detectable in that part of the spectrum. There is another reason why liquid water, which is that if you look at the most abundant elements in the universe, the most abundant element in the universe is hydrogen. The second most abundant element is helium. And the third most abundant element is oxygen. No wonder universe makes water, uses water as the basis for this life signature, for life. In my opinion, maybe Sudha has some other opinion on discussing this. It's very likely that we will be able to find water-based life anywhere else. It's just that if you have more of that substance, that's what you will use around you. Just like what we use for construction materials, if you have more of some materials, that's what we would use, right? That's another reason why we want to focus on liquid water-based life. And based on that chemistry, we will find out what kind of biosignature gases we would be able to detect. Because we know how water-based life behaves. We know what kind of gases it emits, and that's what we want to look for. Okay. And so I vaguely define the habitable zone, but how do you define the limits of the habitable zone? Where do you define the inner edge of the habitable zone and the outer edge of the habitable zone? So there are some climate models that you can potentially use and work on. And this is something that we have worked on a few years ago. It's very simple. It's not complicated. It's all you do is you take an Earth-like planet. In this case, we took an Earth that has too much water. I'll come to that why. And then what we just did was we just moved the planet closer and closer to the star until most of the water goes away from the surface. By definition, if the most of the water goes away from the surface, it is not habitable because liquid water habitability, habitable zone. And that limit is called moist greenhouse. Moist because most of the water vapor is in the atmosphere. It's a greenhouse gas. Water vapor is a greenhouse gas, right? Because of all the 3 degrees of freedom that I mentioned before. And so there is a limit. As you push the planet closer and closer to the star, there's a point where most of the water goes into the atmosphere. That's the moist greenhouse. And if you still keep pushing the planet closer and closer, it'll go to a point called runaway greenhouse. And that point is where all the water goes away from the surface of the planet. Why does runaway greenhouse happen? Because at one point beyond the moist greenhouse limit, because water vapor is a good greenhouse gas, it heats up the planet. And when it heats up the planet, more water vapor is evaporated away from the surface. And then as you get more water vapor, it's a good greenhouse gas. It heats up the planet even more. So it's a positive feedback cycle. And then very quickly, the planet goes into the runaway greenhouse limit. And so this defines these two limits define the inner edge of the habitable zone. Okay? We use a climate model to do that. A simple example is here, a plot of water vapor mixing ratio. You can see it's about 10 to the 4, 10 to the minus 3 here. And this is the altitude in kilometers, how the water vapor profile is changing. This is a simple model that we use. And these are different temperatures. At one point, as you go, this is 280 Kelvin, 290 Kelvin, or whatever, that 300 Kelvin. And then from 320 Kelvin to 340 Kelvin, you'll see there's a big jump in the atmospheric water vapor at a certain point. And that big jump is where the moist greenhouse happens. And at that point, it's inner edge of habitable. Yes, Subbu. I want to say yes and no. So this particular model, the way we define habitable zone is a nitrogen-dominated atmosphere, just like Earth is, and a water-dominated atmosphere without oxygen. Now, N2 and H2O. Now, why did we do that? Why not just use Earth and then do whatever we want to do, right? it is a fully saturated atmosphere. That is what more water vapor means, because if you use this kind of a model of saturated water vapor, you will get the most conservative estimates of the habitable zone. Okay, the most smallest habitable zones that you can get. And that's what we want to go for. If you use an Earth-like atmosphere, there is not much water vapor. So maybe you can push the planet a little bit even further closer to the star. But that gives you a wider habitable zone. So your question may be, why do you want the most conservative habitable zone width? Why do you want the most smallest one? Because we want to know what is the smallest possible habitable zone that you can get. And then from there, you can expand habitable zone with whatever the, compounds you can add in. And that's important for mission designs, because if you know the most minimum amount of habitable zone width, you can design a mission saying that, okay, I want to build a telescope mirror that can detect planets, life signatures inside a habitable zone that is at least this much. And then I can go ahead and then build other instruments later on. Another reason is that the most conservative estimate also gives you the most biggest telescope. Because if your habitable zone width is the most smallest one, and if your star and the planet system is much further away, it's hard to see a planet within this most conservative one. So you have to build a big telescope to look that far. And that's why we want to build the most, we want to be most careful. We don't know what the universe is going to give us. And that's why we want to build the most, one of the largest telescopes to actually find. We don't want to miss any life signatures, even in the most smallest habitable zone width. Does that, boom. Did I say something? Correct. Water becomes yeah. Yeah. Innermost. So I'll come to the CO2 atmospheres for the outermost habitable zone calculations in the next slide. However, I'll address that question also, CO2 one. What happens if your CO2 dominated atmosphere to the inner habitable zone? That's what happened to Venus, right? So if Venus, what happened to Venus was essentially probably this. There are debates about what happened to Venus in the first place. Some say that the Venus was formed right from the beginning with no liquid water on the surface. It was always a steam atmosphere or magma ocean. And then most of the water was already in the atmosphere when it formed, and sun's UV radiation, because it was active at that time, many billions of years ago, split water molecules, hydrogen escaped, oxygen came down, and Venus never formed, had water at all. That's one possible hypothesis. The second one that we have, a lot of people believe, again, I say believe because there is no evidence to anything yet, is that this happened to Venus. Eventually, probably what happened as the sun's luminosity increased, because sun is a main sequence star, so the luminosity increases, right? As the luminosity increased, the amount of radiation on the Venus, because it's closer to the star, right, also increased, eventually heating up the planet. And probably Venus had water before, and most of that water went into the atmosphere, went into runaway greenhouse, and it was just gone. That's the second hypothesis. Yeah. CO2. And so once the water went away, volcanic activity emitted CO2, and hydrogen sulfide, sulfur molecules are still in the Venusian atmosphere. Is post runaway greenhouse state. Yeah, yes, the plate tectonic, so that's another thing. So the eventual volcanic activity emitted all these CO2 gases and sulfur molecules, right? And also it doesn't have a magnetic field. And some people claim, maybe some of you know this, claim that the reason why Venus also doesn't have magnetic field and doesn't have water is because the water is a lubricant probably to have a plate tectonic movement potentially, or even the sun's luminosity probably evaporated even the mantle water completely. And so even the plate tectonic movement stopped. And so if there is no plate tectonics, there is no carbon silicate cycle weathering. We'll come to that later on. And so Venus is not habitable. So there is a way to push the planet into runaway greenhouse state without water, but only CO2. We are doing that right now to our planet, right, by pollution. And so we actually did this study back in 2014. You dump as much fossil fuel CO2 emitted into the Earth's atmosphere and see if you can push the planet into runaway greenhouse. You won't. You can't. But then we don't have to wait until that point. We will be dead much before that. I mean, we'll be dead by moist greenhouse temperatures, 320 Kelvin. I mean, I can't bear my Vijayawada temperature itself, so I don't know if I can do that. Radius value, yeah. Correct. Yeah, Subodh is good. So runaway greenhouse effect could be possible in some of these planets. I have a couple of backup slides on how do you test the limits of the habitable zone observation. I will come to that in a minute. And so that to answer the question about the radius valley gap, that is possible a way of transitioning from a super Earths to sub-Neptune super Earths to terrestrial planets, because the photolysis probably is quite small. The time scale probably is quite small. That's why there could be a gap. It is more intense around M stars, actually. Yes.
So this model start with initial profile, and then the model evolves to radiative convective.
Yeah, so ideally, yes, that's exactly what happens. We try to do the flux balance along the altitude, and then these profiles are actually generated from the convergence model.
So then the process, suppose you start with H2 profile initial, and then your PT profile will evolve. So your again the H2 profile will also evolve.
That's
so. And this is an evolution, or this is the final result that surface temperature has been 320, 240?
So we define the temperature because it's an inverse calculation. Okay. Yes. So we said, okay, if I want this kind of a temperature, what would be the water vapor profile? We can potentially do this in the way you are suggesting, where you can take the model to a convergence and then do it. Unfortunately, what happens is the two-stream radiative processes in the model crashes at these beyond these temperatures. Because
how do you tell them? Because it can be anything you want to do that.
So it's imposed condition. So we impose conditions of the temperature. And then we'll say, okay, to achieve this temperature, what would be the radiative balance that you should get at every layer? And then even by the end of the top of the layer, it has to be energy balance, right?
This is the radiative balance and
surface temperature, because that gives both constraints, that tells you what kind of a profile, water vapor profile you can get.
That case also, it's very challenging to get the convergence.
It's pretty, I mean, you don't have to go through there is no convergence here, because you just need to mention that, okay, go through the radiative convective model, forget the convergence, but just tell me what is the water vapor profile. Because if you do the forward model calculations to do the convergence, it will go up to 340 Kelvin, but beyond that, the radiation tables for the Hytron and they just crash. The two-stream radiative code, the Jacobian matrices, they just fail. So, and that's why people have tried to do this in the forward model, but what we did was just did the inverse model specifying the temperature and the radiative balances at the both thing. Yeah, is that okay? So, yeah, go ahead.
With the carbon.
Yeah.
Takes it out. Is there any
When the surface is solid, isn't that what happened to Mars? Right. So Mars, for example, Mars has a different problem. Venus was about Earth size, Earth mass. And the problem with Venus was sun's radiation increased and removed water, whatever. With Mars, the problem is it's a smaller size. Smaller planets lose interior dynamo pretty quickly. That interior dynamo creates a magnetic field that protects the atmospheric escape, right? And so what happened on Mars, there was liquid water because we can see dried up riverbeds on Mars. And eventually it lost its inner dynamo heat. And so the core stopped rotating and then the magnetic field went away. And sun's radiation just was waiting there to remove the water vapor or water on the surface. And then the hydrogen escaped, oxygen, went back into the crust and rusted out the surface, and that's what we see right now.
Right. No, I guess I lost much. If you have a magma surface, and you free oxygen reacted to the carbon, you get a separate feedback loop, and the CO2 starts escaping.
Right. So that kind solid surface, you mean? Solid surface with this. What kind of a surface do you have there? It depends on whether the oxygen sink is available or not. And if the oxygen sink is, even if there is an oxygen sink, it should be saturated enough for the oxygen to build up in the atmosphere at some point. And that's a false positive again, because once because you see oxygen, but it's not a habitable planet at all. Yeah. Yes. Okay, so in other kinds of, if there are any other kind of substances that can be there on the planet, and how do we do that? My entire life career was based on water-based life, and as I mentioned, because that's all we know. If there could be another way of doing this with other substances. However, I do not know how those kind of substances would be reacting with okay, it's just nitrogen and water vapor atmosphere. That's it. Because that's like I mentioned, it's the most conservative habitable zone that we are trying to do. There were papers that discussed about hydrogen habitable zones as well. And they do talk about what happens to the limits of the habitable zone. They have hydrogen and still they use water there though. I mean, you can't escape water anyway. There were, I think those are these water vapor and hydrogen habitable zones are the only two that I can think about any other compounds that can be used for habitability limits. Does that answer your question? Yeah.
Carbon dioxide. Yeah. Because if I'm not wrong, at higher altitude, it's actually could prevent
I'll come to that in a minute. All the rights of the habitable zone. Thank you for doing it. Someone else also had a question. Yeah. No, there is a temperature profile we define, an Earth-like temperature profile we define. Yeah, because they're standard, we use the US standard atmospheric temperature profile for this. No, not in this model. So that's what I was saying, that we have tried and other people have tried to do this convergence. And at that time, when we published this paper, the model was not able to do it. But in the last 2 or 3 years, some of our students have tried to do this convergence, even in the forward model calculation, by actually calculating the pressure temperature profile and trying to get the water vapor profile from there. and the results are not too dissimilar from this. No, this is a radiative convective equilibrium model. So this is not a photochemistry. In the photochemistry model, where you use you can use a chemical equilibrium model as a starting point, and then you let the photochemical model to converge to get to whatever the mixing ratio values you will get, right? And so you don't need anything like that here, because there is the converge, the radiative convective model will do the work for you. In fact, the photochemistry model needs a pressure temperature profile, and you give that pressure temperature profile from this climate model. And then you can do a coupling. First run the climate model, create a temperature profile, and then give it to your photochemistry model. Yeah. Can you speak out loud? What do I start with? Okay.
The initial abundance, how do you start the model?
Nitrogen and water vapor.
Yeah, I mean, you know that from Earth, like Earth has that kind of, so.
Right.
So in a sense, you are biased.
Well,
like you already know what Earth has.
Yes, not only that, it's not just bias, there is no other option for us, because you look at the compositions of all terrestrial planets in the solar system with atmospheres. Venus, the most dominant atmosphere is nitrogen or CO2. And Earth, nitrogen or CO2. And sorry, nitrogen and oxygen. Mars, nitrogen or CO2. Titan, also terrestrial planet, nitrogen and methane compounds. And so every terrestrial planet within our solar system that has an atmosphere has nitrogen as the most dominant or the second dominant gas. There is a reason. I mean, universe is telling us, look, you can't escape nitrogen. And so nitrogen is there. And yes, nitrogen bonds are hard to break. I mean, that's, I mean, there is a reason why it's accumulating, right? It's a triple bond. From the mantle outgassing, secondary atmospheres, all these are secondary atmospheres. Or it could be impact generated. Impact generated could also create different kinds of composition. But I think much of the thing is from the secondary outgassing. When I say secondary outgassing, many of you probably know this. Primary composition is from the solar nebula that Subbu talked. You can accumulate hydrogen and whatever other lighter gases. Eventually, photoevaporation removes the atmosphere. Or Earth shouldn't, if it should end there. But then the interior processes creates a secondary atmosphere by volcanic activity that releases nitrogen. It releases all gases. They all react except nitrogen. There are geologists who have probably tried for the Earth's interiors, and I think they have been successful in explaining at least the Earth's case, probably or the Mars case. Now, Venus, we don't know much because we have sent only very few probes over there to actually know anything about much of that. So we are learning all from our solar. We are building everything from our solar system planets. In fact, if not for this runaway greenhouse process for Venus, at one point in the history of our solar system, we would have had 2 habitable planets, or 3, including Mars. Mars had liquid water on its surface. We have this evidence, right? And so imagine. So habitable planets are probably potentially common out there. It's just that, we have only one. If you ask this question, how many, if Earth is habitable, how many habitable planets are in solar system? 2 billion years ago, I would have said 2 planets, Venus and Earth. Who knows what happened at that point? Maybe they had a civilization at that time. Someone was giving talk like this. All right. So someone was asking about this CO2 condensation. There is outer edge of the habitable zone, just like we did. Oh my God, we spent so much time in the inner edge of the habitable zone. All right. So outer edge of the habitable zone. The same thing we can do where you take the planet further away from the star, and you'll find this funny. When we take the planet away from the star, we keep dumping CO2 in the model to keep the planet warm, just be alive. And then so we keep dumping CO2 into the planet, but there comes a point where CO2 starts condensing as a cloud, because it's getting cold. Even CO2 is a greenhouse gas. We know this. And it starts condensing. And if you keep taking it out further away from the star and keep dumping even more, there comes a point where no amount of CO2 will warm the planet because the planet cannot take it anymore. And that's called the maximum greenhouse limit. That's the maximum amount of greenhouse you will get. That defines the outer edge of the habitable zone. Okay? And so these two limits, the inner edge of the habitable zone and the outer edge of the habitable zone, gives the habitable zone limits. All right? And then we can use these habitable zone limits. And so anyway, this is what happens as you increase the CO2 partial pressure, the amount of radiation that's escaping from the planet eventually flattens out because there's enough dense CO2 that there's no more warming happening. The ratio of this defines the maximum greenhouse limit. And if you use those limits, combine them into a figure, ask a colleague to make this cool plot, that's what you'll see here. Okay, what's this showing? This is the amount of starlight the planet is receiving relative to the Earth. 100% here means that's the amount of light the planet is receiving exactly as Earth. Okay, 125 means it's receiving 25% more in flux, stellar flux. 75% is 25% less stellar flux. And so, and you can use that method for all different kinds of stars, stellar temperature as a function of the amount of radiation, and that gives you the habitable zone limits. There are several different limits here. This is the most conservative habitable zone limit width that I was talking about. And this is an extension of the habitable zone limit called the optimistic habitable zone, the whole thing from here to there. And that's based on how Venus could have been habitable 2 billion years ago when sun was about 25% less luminous. And so depending upon where you are, which habitable zone limits you want to use, you can claim potential habitability of your favorite planet here. And there are claims of that as well. Almost all the exoplanets discovered so far have used these habitable zone limits for consistency reasons. What's unique about this plot? You can see the clustering of planets around smaller stars. Most of the habitable zone planets are discovered around smaller stars. Why? Because smaller stars have planets closer to them. They have short orbital periods, higher signal to noise ratios, so you can spend less time and get more out of them. And that's why we found more of them. And Kepler, that Subbu discussed, did discover a couple of these. This is Kepler 62f. Some of these habitable zone planets that are slightly larger than the Earth, but no habitable zone planet around a sun-like star yet.
Are these from the confirmed?
Confirmed. These are all. Yes, these are the confirmed habitable zone planets from the NISER database.
That's either transit or
everything. In fact, GJs, all GJs are radial velocity planets, I believe, right, Joe? Many of these are Teegarden star is, it's controversial, but whatever. TRAPPIST planets, these are transiting planets. Kepler are transiting planets. GJ are radial velocity planets. Ross is radial velocity planets. All these are. It's the radial velocity or transit, the orbital period is it's more easier to detect. So all of them are confirmed habitable zone planets so far, right now. Even Proxima is here, I think somewhere there. Yeah. Yes, it is 100% for Earth. In fact, if you draw a straight line, that should be Earth. It looks like that, but because the size of the planet I put in, it is actually right at the 100% one. I think this curve is making it look like it is not at 100% visual aids, or eyes are deceiving. Is that what you're asking, right? So if I remove this curve and draw a vertical line, probably you'll see it's right bang on. That's an optical illusion. Yes, I know you're trying to measure it, but that's, believe me, maybe we'll print it out and then we'll do it during lunchtime. And so this is the runaway greenhouse limit and so on. And Subbu, you were asking something. 452, it is slightly not exactly sun. Not in the line, but I have to be, be very precise. People are asking if Earth is right. It's 5,500, not 5,800. So that's why it's sunlight star. Okay. Oh, okay. Any other questions? Cool. All right. Okay. If I do this in the orbital period and planet radius plot to see where the habitable zones are for different kinds of stellar spectral types, this is the orbital period regions that we can get. And you can see I used a little bit older data, but I used more updated data than Subu, who showed 2022 data set. All right. Okay, so here is the habitable zone planet region for in the orbital period days. That's the stellar flux one. So if you find essentially hab zones for M stars is probably around 8-10 days to around 100 days or so. Still, there's an overlap here, and that's good. Proxima Centauri is in about 11-day orbital period. I think it's a radial velocity planet, and so that's important. They have other problems. We'll come to that later. Okay, so how common are potential habitable worlds? Using these habitable zones, what are these habitable zones used for other than target selections? We can use this habitable zones to define how common are potential habitable worlds so that we can build a telescope that's appropriate size. So based on some estimates, this is actually a number I converted on that. It's about 2 billion habitable zone planets in our galaxy for sun-like stars. Okay, ask me how I reached this number. All right, later on. Okay, no, Subu. I know. We'll have a lunch conversation on that. Okay. All right. So the way we define the occurrence rate of these planets, habitable zone planets, is something called the eta Earth. This eta is different than what Subu mentioned regarding the gas velocity efficiency. But there is an actual document that did this back in 2008 when they were at that time designing an actual telescope called Terrestrial Planet Finder to find Earth-like planets. In that document, they defined eta Earth as, we've called this frequency eta Earth as the fraction of sun-like stars that have at least one planet in the habitable zone. That's where the habitable zone comes, where they define. That's it. So it is a fraction of stars that have at least one planet in the habitable zone. That's the definition of the eta Earth. So if someone wants to define how common are habitable planets, you evaluate this eta Earth based on the number of planets and how many planets are in the habitable zone. And that is why habitable zone is important to define this. And why should we even care about this eta Earth? Because Subu talked about Kepler statistics. Kepler, what is the first primary mission of Kepler? Is to actually calculate this number, eta Earth. The whole point of Kepler mission, the primary mission, is to find how common are habitable zone planets around sun-like stars. Okay, and that's the reason why we want to find this. And where does this eta Earth come from? Many of you probably know Frank Drake and Drake equation. It's an equation that gives you how many communicating civilizations are in the galaxy, because Drake was a radio astronomer and radio astronomy and SETI started way before. And so they started defining what are the factors that you need to have to find out the number of communicating civilizations. And in that, one of the quantities is the rate of star formation, the fraction of planets around a star, the number of planets that are in the right zone, and the fraction of those planets that have life, the fraction of those planets that have intelligent life that could communicate, and the lifetime of the civilization. Okay? And so there is not an exact eta Earth factor here. Essentially, it is a combination of this fraction of planets and the number of planets that could have life on them. Together combined is the eta Earth. That's where the Drake is. So we can use this Drake equation to find out how common are planets. In fact, we are slowly finding out each and every factor in this Drake equation. We already know the rate of star formation. I think it's a couple of 10 stars per year or so. Astronomers correct me. That's what I know. 1 solar mass per year. There you go. And the fraction of planets we already know from the every star has on an average 1 planet around it. So that's 1 factor. FP is 1. And eta Earth is essentially a combination of these two. So I'll come to that in the next few slides. And once we build a telescope that can find the biosignatures and techno signatures, we will know FL, FI, and probably FC as well, all at the same time. The lifetime of a civilization depends upon what they do. Okay. All right. Where is it? Okay. So here is the eta Earth for different spectral types. This is from a paper that was recently published. Eta Earth, depending on the temperature of the stars. As you can see, it is very uniform, which shouldn't be, because we should have a trend. And so if I ask you, can you tell me the eta Earth for a K dwarf or an Earth G star, you would have a hard time to tell it, because it's all over the place, because it's all error bars and everything, right? And so how do you find that? So this nice paper by Rachel Fernandez, they combined all these estimates together, because each paper was using different radius of the planet, different orbital periods. Someone were using optimistic habitable zone that I mentioned. And so they combined all this together and then made this plot. And if I can narrow down where most of the error bars line up to see where the most eta Earths are there. For G stars, for sun-like stars, I would say the eta Earth is probably around between 0.2 to 0.4 if I can overlap with most of the error bars in this region. Okay, and for M stars, it's even better, or maybe worse, depending upon what I'm going to go back here. It's an order of magnitude, and so God save us. I don't know what to do with that. No, eta Earth is for every. The eta Earth, how is it defined? It's the frequency of at least 1 planet and sun-like stars, but then we use it for M stars as well. Sun-like, because they were focusing on TPF, which is a terrestrial planet finder focusing on sun-like stars. And so you can do the same thing for M stars as well. Okay. All right. Okay, that's what I would say if someone asks you, what is the eta Earth? That's what I would give a number on. Okay, so we haven't even touched the biosignatures yet. So for biosignatures, there are some questions that we can address based on what life can produce, what kind of data we will be collecting, and how do we quantify the uncertainty. Someone was asking about the evolution of the gases in our atmosphere. This is how the major gases in our atmosphere evolved over the last 4 billion years. You see the CO2 and methane were the most dominant gases in the first few billion years. There was life, but there was no oxygen, right? And so, and eventually oxygen evolved to the point where large organisms started forming at around 500 million years ago or so. And so this is very critical. Someone was asking about what about the age of the system if we want to know. Well, this is what it took for Earth to come to the complex life. It took about 4 billion years to come to the complex life because of various, geochemical mechanisms. There is no reason for other planets to follow this cycle. Absolutely no reason. Okay, and that's because the luminosity of the sun changes. The Earth itself has a mechanism to control its carbonate silicate weathering process. And so this is unique to Earth. But half the time in the Earth's history, there was no oxygen, detectable oxygen. Okay, and so there is no need for organisms to evolve at the same time. In fact, oxygen is required, apparently, for complex life development, because oxygen provides the largest energy source available for metabolic activity. Abundant oxygen is necessary for higher energy demands for complex life elsewhere, anywhere. So eventually we'll see that not just for biology, even for technology, we will need oxygen. It all comes down to energy usage. Anything in the universe has to have availability of, and it depends on the availability of energy. And you'll see in a while why that is so. And so we published a paper last year, an independent link, completely different to this, that there is seems to be some link between Earth's oxygen level and geomagnetic magnetic field in the last 540 million years. I think probably a complicated plot would be more better here. Okay, so here is the time in mega years. So it's in the past 540 million years is here. This is the present. This is the amount of oxygen in the atmosphere. So today's level is about 21% or something. So that's why, you'll see somewhere over here. Oh, sorry, here, 21% or so. And then this is on the y-axis is the magnetic field. Yeah. Are you talking about the habitable zone definition or? Yes, I knew this. But what about the magnetic fields? That's the question. Yes, so it was not considered at all. And not even the atmospheric retention of that considered at all. Yeah. Okay, so, and here is what happens. Even we see that around in the last 540 million years, there seems to be some correlation between the red graph, if you call it, and the blue oxygen evolution. And at some point, they seem to be peaking around the same time. And that's the point where the Pangea supercontinent apparently formed, was existing at that time. And there seems to be correlation between where supercontinents are forming and where oxygen is peaking. In fact, you see oxygen level, the blue shaded curve, at some point reached 35, how much time I have? 16 minutes, all right. It's reached 35% of the atmospheric level. Today, it's 21%. At that time, it's 35%. Everything was burning because oxygen, right? And why did it stop at 35%? Because there was nothing else to burn after that. And organisms grew in size in this region at this time quite a bit because they became large. There was more oxygen availability. And so the Pangea supercontinent was the last supercontinent. Eventually, it's essentially all the continents right now joined together. And the continental split happened. Around that time, probably some geomagnetic field, there was influence on the geomagnetic field because of this continental drift. And as you know, India drifted and collided with the Eurasian plate that created the Himalayan mountain ranges, okay? So this is probably what happened, maybe the reason why we see this relation between these two here. So there are different pieces of the puzzles occurring and appearing everywhere. So there are different kinds of biosignatures based on whatever we have discussed. And if you look at a planet like this, if we take a telescope and look at an exo-Earth, this is what we will get with the current technology. We won't get like what you see in Star Trek with a nice spherical structure, oceans and all. We don't have that kind of technology yet. And so if someone says, I want to find Earth-like planets, great. Which Earth do you want to find? Do you want to find the Earth that was 4 billion years ago with no oxygen, but still had life? And it was orange, probably, because it had hazes. Or do you want to find the current Earth? Or do you want to find something like Venus, we will eventually evolve to? And so Earth's structure and color was completely different. And the spectral features also change as a function of the time. And so when someone was asking, what about the age of the system? When you look at a planet, you could find a combination of this or nothing of this. So you have to look at this kind of spectral features and try to figure out what kind of gases are there. By the way, I didn't even include error bars here. None of the spectra look like this. If we look through a telescope, I'm sure the astronomers know this, nothing will look like this. It will be filled with error bars. And so we have to be really careful. There was hazy period back 2.5 billion years ago, and the spectrum should show a Rayleigh scattering in the current atmosphere, but it doesn't show there because the haze mutes it, okay? And then there are different kinds of biosignature gases we can detect based on different periods of the time. You can find hazy atmospheres with methane and CO2, but no oxygen, as I mentioned over here. However, there is also an interesting period of time in the Proterozoic Earth where there was oxygen levels are pretty low and ozone levels are pretty low. Ozone and oxygen, we need to have both of them together. That's the UV shield protection. And this level of ozone detection is kind of hard with the kind of telescopes we are trying to make. But that's one of the, but there was still life. That's where the Cambrian explosion, happened. And this is the current modern Earth atmosphere where we have strong ozone signal in the UV band. This is in microns, 0.5 micron, 1 micron, and so on. And then oxygen feature, sharp oxygen feature, several water vapor and CO2 features as well. A combination of methane and oxygen is a really good biosignature. They should not be together. If we see them together, we need to come up with an explanation how and why they are existing. Titan has a lot of methane, very little oxygen. Okay. But we don't know if there's life. All right. And the same thing happens for other kinds of biosignatures. There is sulfur biology. Sulfur compounds also are released by biology through direct and indirect processes. You probably have heard about dimethyl sulfide. I'm sure Madhu will talk about this next week. There are some indirect processes where biology could emit with dimethyl sulfide. There are no known abiotic processes that I know of. Maybe some of you know. And they are produced in an anoxic environment of early Earth. And so, but just this chemical is not enough. Like I said, you need to have other chemicals as well. So for example, if you see dimethyl sulfide and ethane, where do you get the ethane from? The dimethyl sulfide, which is this chemical process, can be split into these radicals, CH3 through photolysis, and two CH3s can combine to become ethane. And so if you see dimethyl sulfide and ethane together, things get interesting. Then talk to us. Then maybe there is an interesting aspect of that. And so we will see what Madhu says. I'm going to leave it at this. Okay. This is a reflected light spectra of Earth, current Earth, as a function of wavelength and brightness. There are several features of where different kinds of things are happening. Vegetation. Over here, the Rayleigh scattering, blueness of the sky, methane features, water vapor. Earth is full of water vapor. And there is one unique feature that we can see, which is called a vegetation red edge, because in that part of the spectrum, trees, plants are quite reflective in the near infrared. And this is a photo in the near infrared of the same tree. And so if you are infrared sensitive, this is what you would see from the far. If you have the resolution, not only you can also see how Earth is rotating and see in different bands, find these spectral features and plot them. I call this the breathing Earth. Because as a function of time, you can see how the spectral features are changing. That tells you about if there are continents on it, oceans on them, reflects deserts, reflectivity, everything. But this takes time, right? Because it's a long observational time. Same thing happens if you want to do this over the many months and so on. You will see that as the planet is rotating, you will see things changing in the different parts of the spectrum. That tells you something about where the continents are located, where you can even think about how the obliquity of the planet is changing, because you have your models to discuss about it. Right. That is why we don't do this in transit or things. There are many transitors here, scientists. I am not a big fan of transit technique, because transit technique is used only because right now it's the most easiest one to detect planets and their atmospheres. The real one we need to do is direct imaging. That's hard to do, which we are trying to do. But transit technique was developed because you just need a small telescope, point to a star, find the, whatever, and then get the signal. Transit technique is also limited to only the most top part of the atmosphere itself. This one actually tells you reflectivity. There is also degeneracy here, depending on albedo and the radius of the planet. Right. Does that answer your question? Why flux is increasing? Or let me see. I think this is over time in the orbital period of the planet. This is changing. You're coming more and more into the view of the observer. Yeah, because look at this is whatever the number of hours. 24 hours is 1 day, so it's like 240 hours is 10 days. These are months, and so as the year is progressing, you would see more and more. Correct. How? Yeah. Can so what the way we do direct imaging is we block the star, and the light impinging on the planet is what we resolve into spectra. Yeah. Then that's also a seasonal activity, but the activity of the star itself will affect the atmospheric chemistry of the planet, and so that will affect the features, the spectral features, and the flux as well, probably. Yes, someone raised it. So that. It is going down completely here at the edges. You're asking why is it going down completely, or why is it peaking between? I think day-night variations. First of all, these small variations are probably day-night variations. Right. It's the I think it's probably the amount of time the planet is taking to go. So maybe in this particular simulations, the simulation probably started with where the star is here and the planet is here, where not enough sunlight is there. And then it's probably 600 hours is how many days? Some days. Yeah, different phases. And as you go, different phases there is more sunlight on that not even one full phase. Oh, sorry, you want me to one at a time? Yeah. Oh, okay. We see it. Yes. That's is it. Why is it not playing? Okay. I think there will be light. There you go. And at the peak of the one, you'll see the maximum phase angle of the planet in that orbit. I didn't actually pay attention to that sphere over there. I was just looking at it. So now you'd see, because it's a more reflected light, right? So it's about a month, yeah. 600 hours is, it's about a month. Yeah, about a month. Probably, Jake, I'll ask Jake what's going on with this planet. But this is how, I mean, the demonstration is to show that this is. Can you speak out loud? Yeah, it could be. I have to see what Jake used for this one. Let me see what he says, then we'll come back to that. Okay, now we will go back. I got 5 minutes to talk about techno signatures, my favorite topic, my God. All right, habitable planet with technology. Just as biosignatures, we can also detect techno signatures as well, okay? And we will use, to find techno signatures, the same kind of technology that we are using on Earth. That's what we did for biosignatures. Why should it be so different? We can't even figure out what's a different biology is. How can we figure out what a different technology could be? And so there are several ways to do this. We call it SET-T, search for extraterrestrial technology. Why? Because we cannot detect intelligence remotely. We can detect only technology. I can't detect intelligence even closely, so forget remotely. So this is a search for extraterrestrial technology. We want to, technology is trying to detect technology, and that's what we want to do. There are different kinds of things. You probably are very familiar with this kind of radio city searches. There are a couple of papers that some of my colleagues published. How do we detect city lights similar to the planet variation that we just talked about? Megastructures, I'm not a big fan. Laser pulses, a student of mine is trying to do. He found an unusual one. Let's see if it comes out to be true. Surface structures, you can see ISS modeling. We try to do this to see if we can detect this. Probes, a civilization could send probes. We are doing it right now. We sent Voyager, we sent Pioneer probes, New Horizons, even Breakthrough Starshot, which is trying to send a probe, a small microscale probe with light sails, a 1 meter kind light sails, by shooting laser pulses on it. Thousands and thousands of them towards Proxima Centauri, so that it can take a picture and then they'll just go away. I mean, I don't know if someone from Proxima Centauri is sending thousands of probes to my planet and then, want to take a picture. I don't. It's in whatever. It's in suspension right now. Okay, but then the probes technology is actually valid, because if we can do it, they can do it. Probably already did it. If we can build big telescopes, they already know. Some of them are very concerned that, why are we doing Radio City? Don't send communications. They will come and attack us, Independence Day, whatever. Okay, listen. It's like a small kid trying to hide by closing their eyes. Okay, if you suspend all the radio communications today on Earth, they will still find us, because they have other wavelengths, like the terrestrial planet finder. They'll build a telescope, find the spectral features, and then they'll see, okay, there is a planet here. So whether you build a radio telescope or send signals to other planets is immaterial. They will find us. They probably did it already. Okay, so what kind of technology we can detect? Pollution. We can detect pollution in the atmosphere. It's a passive search. They don't have to do anything. They can go on about their daily life of polluting their daily atmosphere and then, do whatever they want to do. And then we can detect the pollution. How do we know that? Because during the COVID pandemic, we saw that the pollution or the nitrogen dioxide emission, which is emitted by fossil fuel burning, decreased significantly by about 20 to 40% over urban areas around the globe. This is just the US. And so we thought, oh, wait a minute, I have nothing to do in COVID. So how do we detect this technology now? Let's find a paper. And that's what we did. Okay, and so now we think LUAR is the kind of telescope that's the big direct imaging telescope that we would try to do. And apparently we can detect this technology, pollution in the atmospheres, with the same telescope, with the same instruments, same methodology, same models that we use for biosignatures. We can use the techno signatures as well. That's the idea that we want to propagate. Chlorofluorocarbons. Many of you probably know this. They are very dangerous in terms of ozone depletion, used in refrigerants, in some refrigerants. James Webb Space Telescope. Jayesh may be interested in that. Let me know if you find anything CFCs, Jayesh. You can potentially do on TRAPPIST planets if they exist. The point here is not, why would they do these emissions? Why would they pollute the planet? Or why would they exist? Why do these gases exist on these planets? The point here is, do we have the technology right now to detect technology? Can we demonstrate that one? Whether the motivations of aliens, why would they do it? Their opinions and their feelings are immaterial. Do we have the technology right now or not? We do. So it is not science fiction anymore. It is actual science. Not only that, to build technology, we need oxygen, just like we need oxygen to find complex life. Because open air combustion, I'm done, sorry. All right, open air combustion, to build technology, we need to do metallurgy. We need to burn things, weld things, to burn things, right? For that, you need a minimum amount of oxygen in the atmosphere. And that's the reason why we have the technology we have right now at this period of time, because it exceeded 18% of the oxygen level in the atmosphere. Okay. And there is also another paper that came out recently. By the way, I'm organizing a talk next April 8th by this author, why he thinks that coal deposits are the most important things for developing technology on any planet. Because any civilization that wants to develop into a larger and larger to grow into a technological advanced civilization, it needs energy utilization. And it needs energy utilization in a compact form. So we started with the wood burning, then we went to the coal burning, then we went to fossil fuel burning. Now we are going to fusion energy. And you can see the energy density is getting higher and higher for us. And so if we want to find a technological planet, that planet must have oxygen. There could be, technology can actually migrate to other planets. We have lots of technology in the solar system. We have more techno-signatures in the solar system than biosignatures. We have technology on Mars. We have technology around Jupiter. We have technology beyond solar system, as I just mentioned about the probes. And so technology doesn't need to be constrained to the planet, but the origin of the technology of a planet needs oxygen for combustion purposes. If you have time, read this book. It's amazing. That's where I got all these ideas from. Okay, last one. Everything in the astronomy ever, if you want to find life, not everything, most of the things, we will discover the most strongest, loudest of the class first with the most sensitive instrument, which is unlikely of the population. It was how we discovered the most things. Look at the sun is the first star we ever discovered, but it is not the most representative of all the stars, right? And it's also unique in the sky. Look at this discovery. The first pulsar planets, exoplanets, pulsar planets, they are not the most common planets in the galaxy, but that's the first one we discovered. It's the most strongest and loudest with the most sensitive instrument, radio telescopes, right? The next one, exoplanet, 51 Pegasi b, hot Jupiter planet. They are not the most common one. They are not the representative of all exoplanets, but they were discovered first with the most sensitive instrument, which is the radial velocity technique, which Otto Struve mentioned it in 1952. The first exoplanet atmospheric detection, sodium. That's the most strongest one at that time. Later on we discovered, but that was the first one discovered, but it's not much common around all the planets we see. The first black hole, the first radio source, the Milky Way galaxy's black hole. It's not the most common black hole in the galaxy, but that's the first one we have discovered. The first X-ray source, the first colliding gravitational wave black hole, everything. You will discover, or we will discover, the most outlier first. And so when we ever discover the first life, remote life, it will not be a common life signature across the galaxy. It will be an outlier, and it will not be the representative of it. And so these are some other examples. And so the only way to do that is to find an anomaly, and find anomaly in here. Thank you. Yeah. Where did I keep it? Okay, here. You're talking about Dyson swarms, right? Okay, so that's the picture I showed at, yeah, there you go. This kind of Dyson swarms. And how do we actually know if it is a techno signature or not? Or there was 10 years ago, there was a paper where they thought there was an unusual transiting signature around a star, and that did not match the traditional transiting planet system. And there were papers that claimed that it could be a Dyson swarm or Dyson sphere. What is that tick number? Something. It's a Tabby star, I think, the Boyagin star. That's the Tabby star, right? So okay, so that's the one. But eventually they found out it was actually coming from a debris disk, probably around the star itself. So there are potential ways to identify a natural phenomena compared to this kind of a Dyson sphere. This kind of Dyson sphere does create transiting signatures that can mimic natural objects. So that brings back to my question about my response about building scientific consensus before we claim. It is always good to mention what it is not, rather than saying what it is. Okay, so if you say, okay, it is not a natural cometary dust, it is not something and something, and leave it at that. Don't say it could be Dyson sphere, because then the press will take it and run away. So. Yeah. Okay. Yeah, so there were papers by my colleagues who did work on how to detect deuterium leftover compounds from fusion reactions. Yes, and how do you detect it? Right. In fact, that's the paper, David Catling's paper, D2H ratios, to see how you can find if there's fusion reaction going on. There is also a paper by another colleague of mine, Thomas Beattie, where if you use a fusion as a propellant on some spacecraft, it produces a bright flash. So how do you detect that bright flash, and what could be the signature of that kind of a bright flash is one aspect of doing that. But there could be technologies that are way beyond our imagination. Imagine this, like if I go to, Krishna Deva time and, show my PowerPoint presentation, they're like, what is it? They can't even think. So just like we can't even think 500 years from now what our technology could be. So then the question is, how do you know what to detect? What if you miss it? We will miss it. Even, in fact, we may have already discovered, some kind of life already. It's called inattentional blindness. We just are not familiar. We just can't recognize it, even if it is in front of us, because it's not in our way of thinking. So anomaly detection is the only way, and that's the reason I put that last slide over there. If you see something that's anomalous, that is not conforming to your natural explanation, that's what you want to focus on. Yeah, go ahead. I'm glad you asked that question. So the question was about the dark forest hypothesis. Does everyone know dark forest hypothesis? Maybe, have you read this three-body problem? Yeah. You don't know. Do you want to explain what a dark forest hypothesis is? Maybe give her a microphone. Maybe we can talk about it. I'll have my personal violent opinions about it. So I'll tell you.
So the dark forest hypothesis is basically a proposed solution to the Fermi paradox. Are you all aware of the Fermi paradox?
Can you speak loud, because
Am I not audible? Or should I stand or something? It's fine. Okay.
Yeah.
Okay.
Yeah.
So basically the dark forest hypothesis says that there are intelligent civilizations that are present, but they are hiding out of fear of each other. So the logic is that if we were to find an intelligent civilization, since communication with them might be difficult, all of you must have seen this in the movie Arrival. So since communication will be difficult, it's better to assume that they have catastrophic intentions for us. So we go and destroy them. So the argument is that since every intelligent civilization is looking to kill each other, let's just hide and not send out any signals that could be detected.
Right. So the solution, one of the solutions to the Fermi paradox is the dark forest hypothesis. Fermi paradox, if you probably, yeah.
That's good.
Great filter hypothesis. Yes, actually, do I? Yeah. Yes. Right. So let's see if I have that slide. I don't have that. So in my there are two more lectures I'm giving. Where is Ravinder here? Maybe in my Sunday lecture I'll discuss about this resolutions of, not resolution, Fermi's paradox. By the way, Fermi's paradox is neither Fermi's nor a paradox, first of all. There is actually a paper that literally says Fermi's paradox is not a Fermi's not paradox. It was not, Fermi never said that, where are they? So the Fermi's paradox was, when he was having lunch with people, his colleagues, they asked, if there are so many civilizations out there, why are we not seeing them? Okay, there are so many things I want to say about that statement that is absolutely makes no sense. Why is there a need that you should recognize anything out there? Why do you think you should be able to recognize anything, first of all? And how do you know there are so many civilizations out there? And then the whole cottage industry of Fermi paradox thing started. And then the solutions to the Fermi paradox is one of them is a great filter. The other one is the dark forest hypothesis. The dark forest hypothesis is from the three-body problem books, trilogy that you must read. The character development is atrocious. It's recorded, right? Okay, fine. The character development is not that great, but the physics and the concepts are amazing there. So if you get time, read those books. And the dark forest, one of the solutions to Fermi paradox, why are we not seeing aliens, is the dark forest hypothesis. Now everybody wants to kill each other, so everybody is remaining silent. Okay, fine, that's a good movie to make. Maybe write a good book about it. That doesn't make any sense, because if you assume everyone, I showed you the statistics of billions of planets. I'll come to you in a minute. 2 billion planets. There must be one outlier who could be good, who could be nice, who could dominate everyone and make a kingdom of, a large kingdom of, or an empire like we do in Foundation series or something. So it is, there must be one outlier who is good, that could be, responsible to make everything good out there. Just like we have, you're all listening, some guy who's talking in the back, whatever. There's an outlier, right? And so we should have, I have so many, sorry, my emotions are coming out because of this. I'll come.
Yeah, no.
Oh, which NASA? Which NASA was that? Okay, so we did receive a message from Voyager, but that was in the first part of Star Trek 1 movie. That was a movie. I'm a big Star Trek fan. So that message was not, we did receive a message from Voyager, which is going out of heliosphere somewhere, to still be active and all. The wow signal is a different thing. That came from Ohio State University's radio telescope back in the 1970s, which later the recent paper said that probably is from interstellar emissions. We have not received any alien signals at all so far, officially.
It's one final question before we break for lunch.
Okay. 2 questions. No, but you guys are hungry. I'm hungry. Come on, let's eat. Okay. The Eta Earth. Yes. Yes. Okay. I could have made it. Sorry, maybe I did not explain it very well out here. Yeah, so I tried to overlap all the main detection points and error bars, most of them together. These are from different studies, right? Okay, and so what I tried to do was, okay, I left the outliers out here. I didn't consider them. And I tried to see which of the studies I can cover in the most possible range. And I selected them. I mean, the real value could be somewhere over here. That's why I'm saying I'm going to stick with this. This is a pretty high number. By the way, the Habitable observatory people are probably using somewhere close to 0.2 or less, because it's good to be conservative. You want to have a very low value of eta Earth so that you can big a big enough telescope to look further away. If eta Earth is smaller, that means you have to look further away, much further away to find habitable planets. And so if you see that eta Earth is 0.4, half of it, then you say, oh yeah, Earth-like planets are common, so we'll just build small telescope and look nearby systems. And that's why, so they are using on the conservative side, but I try to overlap with most of the error bars over here to get the range. So whenever someone asks, I'll give the range rather than a number. Someone was here asking, yes. Okay, so that's called the prime directive from Star Trek. In case anybody's interested, I met William Shatner and Leonard Nimoy. Oh my God, sorry. I thought I had that. I should have that. Search for another Earth. So there is, yes, there are one of the options for. Okay, sorry. One of the reasons why we will not be able, why we were not able to detect these Fermi paradox is, I think this is the one. Yep, that's the one. I guess you guys don't have to come to my talk anymore. All right, so there you go. Where is everybody? These are some of them. I'm going to list through this anyway, but please try to attend my talk. I see someone there. Okay, life is hard to arise. That's Fermi paradox reason. Maybe life is hard to arise, so that's why we don't see anyone. Intelligent life is not common. Maybe life is fine, biological life, but intelligent life is great filter hypothesis that someone was mentioning. Intelligent life is not common. Maybe oxygen is needed, right? We just discussed. So intelligent life may not come up. Oxygen and plants and coal are not common, probably. We are not listening properly. My wife always says this. There is a limit to how far life can advance. That is true. There is a great filter argument that we just discussed. We did not search long enough. This is I like this one because if you go to a bus stop and stop there for 2 seconds and come back and say this Bengaluru doesn't have any buses at all because my God, I waited for 2 seconds. That's what we are doing. Our technology, radio technology, developed last 60 years, and as you mentioned, the history of our civilization, agricultural civilization, started 10,000 years ago. And our human technology with tools and all started 2 million years ago, and the Earth itself is 4 billion years. How are you expecting to detect something just because you found a new toy now and you want it right now? Well, okay, don't interfere. There you go, your prime directive. They don't want to interfere because we are too dumb. Hard to travel or communicative or expensive. Maybe it is quite hard to travel long distances. Proxima Centauri B, which is the closest star to us, with our current technology, with Elon Musk's most advanced whatever rockets, will take 70,000 years, 72,000 years to go. Breakthrough star shot that I discussed with the laser pulses, they were aiming at 25 to 30 years with about 10 or 20% the speed of light, if it ever worked. So that's what they're thinking. I don't trust this one because, just because it is difficult for me, it doesn't mean difficult for them. Communicative or expensive. Well, if we spend all our money on wars, of course it's expensive. All right, they want to be anonymous. Who would really want to contact us? I mean, come on. That's one thing. And there are other explanations which I removed here. So these are potential, if you actually believe in Fermi paradox, this is the actual potential resolutions. All right, thank you.